Find the right sentence, not just the right keyword. By the end, you will build a simple semantic search pipeline in Python with sentence transformers. You will see how to compare query meaning to sentences, return ranked results, and combine keyword filtering with semantic re-ranking. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Semantic search matters because it optimizes semantic relevance, not just text overlap. That means higher true relevance when queries use different words than the target sentence. The main trade-off is memory and latency. Dense vectors give better matches but use more RAM and need time to encode a corpus. In practice, a few thousand sentences fit in memory and return results in tens to hundreds of milliseconds. The intuition is simple. We convert sentences into number lists that capture meaning. Queries become numbers too. Then we measure closeness between those numbers. It shines when phrasing varies or synonyms appear. It struggles with tiny corpora, where exact keywords already solve the problem. And with very long documents, where segmenting is needed. We will build a compact pipeline that starts with a quick keyword pass, then encodes sentences with a small sentence transformers model, computes cosine similarity to the query, and returns the top results with an optional keyword first filter before re-ranking. This snippet retrieves the most similar sentence using plain keyword overlap. It runs a simple pass over the corpus, counting shared words between the query and each sentence. The scoring is intuitive. More shared words means higher rank. This is fast and needs no model. You can tune it by changing the minimum overlap threshold. Raise the threshold and you reduce false positives but risk missing paraphrases. Lower the threshold and you get broader recall, but more noise. For many pipelines, this step acts as a cheap filter or a baseline to compare against semantic methods. Now, we will encode the sentences into dense vectors using a compact model. This snippet encodes the sentences into dense vectors with a small model from sentence transformers. It takes each sentence and maps it to a numeric vector that captures semantics. Small models are fast and light on memory, but they trade some accuracy compared to larger models. You can change the model name to a bigger one for better quality, or a smaller one for speed. Another parameter is batch size during encoding. Increase it to use GPUs efficiently but watch memory use, or decrease it to avoid out-of-memory errors on smaller machines. Next, we compute similarity between the query vector and each sentence vector. This snippet finds the best semantic match for the query using cosine similarity, which measures the angle between two vectors and captures relative direction rather than absolute length. The code computes a similarity score for the query vector against every sentence vector and sorts those scores. Using cosine helps when sentence length varies, since it ignores vector magnitude. You could swap to Euclidean distance if absolute differences matter, but cosine is common for text. Also, you could add a score threshold to prune weak matches, which raises precision but may lower recall. Then, we rank sentences and return the top results. This snippet ranks sentences by similarity and returns the top K results. It sorts the scored sentences and slices the highest scoring ones to show to the user. The key adjustable parameter here is K, the number of results. A small k gives concise answers and lowers latency. A larger K improves recall and is useful if you plan a second stage re-ranker. Ranking also supports tie breaking by secondary signals like sentence length or original keyword overlap. If you expect users to scan a list, choose a moderate K. If you plan to display only the best match, set K to 1. Finally, we filter candidates by a keyword, then refine with semantic scoring. This snippet filters candidates by a keyword, then refines with semantic scoring. It first narrows the corpus to sentences that contain a required term or phrase, which enforces a hard constraint like a product name or topic. Then, it re-ranks that smaller set using dense vector similarity to capture meaning beyond exact words. The important parameter is the filter strictness and the re-rank window size. A tighter filter reduces computation and false positives, but risks excluding good paraphrases. A larger re-rank window increases compute, but improves the chance of retrieving the best semantic match. Recap: semantic search converts text to vectors and ranks by similarity. Use it when paraphrase handling and meaning matter. One caveat: it costs memory and needs careful tuning of filters and top K to balance speed and quality. Next step: tune the re-rank window size so you balance keyword precision with semantic recall. If short, practical IR helps, subscribe and watch the IR videos.